that again. Welcome, everyone. Good to see you all. Thank you for coming, and I hope that you had a great weekend and that your week is off to a good start. Thank you again for those of you that have put on your cameras. I see a few new faces up here on the top, so some of you have put your cameras on maybe for the first time, and I really appreciate that. Helps me put a name together with a face, and it also helps me to gauge reactions, like when my speaker's not on, my microphone's not on. So anyway, thanks for being here, and I have a little joke to start off the day. Never trust what atoms say, they make up everything, right? All right. The Zoom jokes never go over well without hearing the audience laugh, so. Anyway, let's see, we have an exam coming up next week, believe it or not, our second exam. Okay, so that's going to be on Wednesday, October 14th, and that's going to cover chapters 4, 5, and 6. Thanks, Megan. And so put that on your calendar and get ready for that. As usual, it'll be very similar to the last exam. Everything leading up to it will be similar, and you guys will be all ready to go. Alexander, you have a quick question?
Yeah, did you hear about what happened that did you hear that oxygen and magnesium got hooked up? I was like, OMG.
Nice. I like it. That's a good one. All right. We are in the middle of our solutions chapter, and we're looking at several types of reactions that happen in solution. The first class that we're going to look at are called precipitation reactions, and that's where a solid forms when you mix two liquid solutions, all right? The second class we're going to look at are acid-base reactions, and that occurs when an acid reacts with a base and they neutralize one another. The general form of these reactions is acid plus base produces water plus a salt, all right? And then the last one we'll look at is the gas evolution reaction, and that's where a gas forms upon mixing two solutions. All right, so we'll be looking at those. You already saw a video on them, so you have an overview, but I'd like to just go over it, and we'll do some examples of each one, okay? So before we get into the reactions, we have to understand a little bit about solubility. All right, and so last time, remember, we were talking about solutions, and we learned that some substances were soluble and some substances were not soluble. Yeah, and so what we're going to do here is figure out how we can predict whether or not a substance is going to be soluble or not.
Hold on, Professor.
Yeah, am I freezing up?
Yeah, you just froze. Repeat like maybe the last 15 seconds.
Yeah, thanks. Yeah, having a little bit of internet issues perhaps. So the first thing we got to do before we get to these reaction types is understand solubility and look over the solubility rules, which help us predict if a compound is going to dissolve or not dissolve when you put it in water. Okay, remember last time we learned that there are some substances like silver nitrate, for example, that dissolve in water, and some substances like silver chloride which don't dissolve in water, right? So we want to be able to predict that. So this little chart here is the best way to be able to predict it. And it kind of tells us, generally by looking at the ions in the compound, right, the cation and the anion, it kind of helps us to tell which compounds will be soluble and which ones will not be soluble, all right? So the top part of this chart, these ions, are compound, if the compound contains any of these ions, they generally are soluble, which means they would dissolve, yeah? And on the right here are exceptions, right? So for example, lithium, sodium, potassium, and ammonium, those ions. If a compound contains those ions, that compound is going to be soluble, right? And are there any exceptions? No. So any compound that contains any of these ions paired with whatever anion you choose, or any anion that's there, the compound's going to be soluble, all right? Similarly, nitrates and acetates, same thing, always soluble. Chlorides, bromides, and iodides, they're, again, usually soluble, but look, there's some important exceptions here. That means that when you have a compound like silver chloride, that's not going to be soluble, right? Because these are the exceptions over here, all right? Sulfates, again, generally soluble, but when they pair with these ions, those compounds are not soluble, all right? The bottom half of this table shows compounds that are, shows ions that when you see these ions in a compound, it generally indicates that the compound is insoluble, all right? So hydroxides and sulfides, generally insoluble, except when they pair with these ions, right? So for example, lithium hydroxide would be soluble, but magnesium hydroxide, for example, would not be soluble, all right? Down here are some more exceptions for sulfide, and then here are some exceptions for hydroxide, and these exceptions are slightly soluble. And that's because we have soluble, we have insoluble, and we really have everything in between. So these solubility rules are a little bit of an oversimplification, but they're very, very useful. For our purposes, especially when predicting precipitation reactions, we can assume that when it pairs with these ions that they're insoluble, okay? Especially for predicting precipitation reactions, which is something we're going to use this table for quite a bit. All right, and then lastly, carbonates and phosphates, same thing, generally insoluble, and here are the exceptions. All right, so let's just practice a little bit predicting whether compounds are soluble and insoluble. So let's start with this one right here. Potassium chloride. What do you think? Soluble or insoluble?
Soluble.
Soluble.
Soluble, right? So potassium, bam, right there. You see potassium in a compound, you know it's going to be soluble. Copper nitrate. What do you think? Soluble or insoluble?
Soluble.
Soluble.
Soluble, right? Again, the nitrate ion, here it is. Always soluble, no exceptions. So it doesn't matter what the cation is. If you see a nitrate in it, it's going to be soluble. Barium chloride.
Soluble. Soluble.
Soluble, yeah. Again, soluble. Why? Here's chlorides. And do you see barium over here as an exception? No, right? So that tells you that this is also soluble. All right. Sodium carbonate.
Soluble. Soluble.
Soluble.
Soluble. Here's carbonate down here. Oops. Here's carbonate down here. And these are exceptions, right? And so sodium is one of the exceptions. Alternatively, you can look up here and you see, sodium. So sodium is always soluble in all of it. Any compound you see sodium in, it's going to be soluble, right? Calcium carbonate.
Insoluble. Insoluble.
Insoluble, right? So you don't see calcium up here, but you do see carbonate down here, and that's generally insoluble, and calcium is not an exception, right? So it's insoluble. Chromium hydroxide.
Insoluble.
Insoluble.
Correct, insoluble, because there are hydroxides, generally insoluble, because they're on the bottom half of this chart, right? And chromium is not one of the exceptions, so that means it's insoluble. Very good. Iron sulfate.
Soluble.
Insoluble?
So the correct answer is it's soluble, right? Because here's sulfates, those are generally soluble, and iron is not an exception, right? Lead sulfate.
Insoluble.
Insoluble.
Insoluble, correct. Because here's sulfates, and they're generally soluble, but look, lead is one of the exceptions, right? Does that make sense? I see a couple of questions. Taylor.
So, are they insoluble and soluble because of what elements they are, or is it just done by experimentation?
Yeah, you're absolutely right. It's difficult to predict whether something will be soluble or not. So these are all just based on observation. So generally, this is a table we call it's an empirical table. It's built not from some theory about whether things are soluble or insoluble, but from what we actually observed in the lab.
Okay.
Great question.
Like, for sodium, we've never found something that is insoluble. with
Correct.
sodium, for instance.
Correct.
Okay.
Correct.
Okay.
Yep.
Thank you.
Francesca.
Should we memorize all of these rules? Or?
Yes. Yep. This is something I'll expect you to know. So if you, so remember you do get a cheat sheet on the exam, so you could use this as part of your cheat sheet, but I would encourage you to memorize this table. Yeah. Good question. All right. Let me have you do one. Go ahead and try this. Okay, looking good. About 10, try to finish up in 10 seconds. All right, very good. A lot of you put D, which is the right answer, so that's great. A few of you put B, so we'll look at why that is not the right answer. So let's look here. We just go through each one really quick. Lithium nitrate, right? Since it's a nitrate, it contains NO3, we know immediately that it's soluble. Also, since it contains lithium, right? We also know that it's soluble from that. Oops. Potassium hydroxide. Some of you put that that is insoluble, but if you look at this, hydroxides are down here, and potassium is an exception, right? Which means that it is soluble. Also, you know that potassium is up here, right? And that has no exception. So anytime you see potassium, that's going to be insoluble, right? Iron sulfate. If you look at sulfates, they're normally soluble, and iron's not an exception, right? Barium sulfate, you look at sulfates, normally soluble, but aha, there's barium, right? So that's an exception, so that tells you that this is the one that's insoluble, okay? All right, let's try one more. Go ahead and try this one. Okay, about 10 more seconds. All right, very good. Thank you all for participating in this. I really appreciate it, and I think it'll help you to learn. So that's the reason I do this, obviously. And on this one, we had, wow, great amount of people getting it right. The right answer is A, ammonium phosphate. If you look at phosphates, it's down here. Those are generally insoluble, but when it pairs with ammonium, it's soluble. All right, so great job. Nice work. Okay. Let's move on. So let's start looking at each class of these reactions. So in a precipitation reaction, you have a precipitate form. And you saw from the video, right, today that a lot of these aqueous reactions are going to have this sort of form where you have a compound AX plus BY goes to something, right? And the key here is to try to sort of say, okay, what happens when I pair the cation from one compound with the anion from the other, and the cation from the other compound with the anion from the other, right? So you're looking at the cross pairing. Why are you doing that? For a precipitation reaction, which by the way, is the reactions that we talked about at the very beginning of this chapter, right? Where you form this solid to encapsulate a liquid, right? In molecular gastronomy, we talked a little bit about that, okay? Precipitation reactions also happen in your bathtub. We produce bathtub ring. That's a precipitation reaction between the ions that are in hard water, like calcium and magnesium, and the anions that are in soap. And they come together and they form this kind of precipitate that is sometimes can get kind of gross. That's why a lot of times you'll have water softeners, right, that soften the water and get rid of the calcium and magnesium ions, so then you don't have this problem. But here's an example of a precipitation reaction in the lab. And what you have here is you have a solution of potassium iodide, right? So you have Ki, right? And then you have lead nitrate, right? And then what we're going to do is we're going to take the cation of one with the anion of the other, right? And vice versa, like that. And we're going to see, okay, are there some products here that are insoluble and therefore will form a precipitate, right? So we can write another column here for possible products. And the possible products are going to be this cation with this anion. So the possible, that one would be potassium nitrate. And notice when I write the formulas for these possible products, I got to write a charge neutral formula, right? Because nitrate is -1, potassium is +1, so I write potassium nitrate. I don't write potassium nitrate 2, simply because there's a 2 here. I got to balance the equation in another way, right? My other possible product is going to be lead iodide, or lead 2 iodide. And the formula for lead 2 iodide is this. How do I know that's lead 2? Because I know nitrate is -1, so we got to go back to our table of polyatomic ions, right? We know nitrate is -1. There's 2 of them, so the lead must be +2. And that means I need 2 iodine. So here are my possible products, right? Now, in a precipitation reaction, what's going to form a precipitate? Something that's soluble or something that's insoluble?
Insoluble.
Insoluble, exactly right. We're looking for a product that's insoluble. So we got to go back to our solubility rules, and we got to say, okay, what's the solubility of these possible products? Well, nitrates are always soluble. So are you ever going to get a precipitate with nitrate?
No.
No.
Never, right? But if you look here at lead iodide, you look at iodides and you see that, aha, iodides are generally soluble, but lead is an exception, right? So this is going to be our precipitate, right? That's going to be our precipitate. And the reason that happens is because of this. Look, when I take this solution of lead iodide, which is a soluble compound, and lead nitrate, which is also a soluble compound, and here's lead iodide, here's lead nitrate. The minute I mix them together, right, look what can happen. The lead ions now have access to the iodide ions, right? And the potassium ion, the lead ions now have access to the iodide atoms. Yes, that's what I meant. And then the potassium ions have access to the nitrate ions, right? Because now they're all mixed together. So because lead iodide is insoluble, these two are going to get together and form a precipitate, right? And you get that precipitate falling out. Okay. All right. Let's look at another example. Here's potassium iodide and sodium chloride. So we do the same thing here. Potassium iodide and sodium chloride. And then we say, okay, what are the possible products? Again, we're going to take the cation of one with the anion of the other, the cation of the other with the anion of the one, right? So my possible products are going to be potassium chloride or sodium iodide, right? And then I'm going to go to my solubility rules. I'm going to say, okay, are any of these insoluble, right? Are any of these insoluble? And what do you think? Is potassium chloride insoluble?
No, it's soluble.
No, that's soluble. And then what about sodium iodide?
No.
Also soluble, right? So neither of these are soluble, so therefore you have no reaction, right? No reaction occurs. When you mix them together, they just mix and no solid forms. Does that make sense? All right, let's do one more example and then I'll have you do one. Write an equation for the reaction that occurs between solutions of lithium nitrate and copper 2 chloride. So now we're back to nomenclature again. Remember how I said this class is cumulative? You got to remember what we've covered before in order to do what we're doing now, right? So you got to remember your nomenclature, right? And how to write neutral formulas for ionic compounds. All right. So lithium nitrate, aqueous, right? Plus copper 2 chloride. So that's CuCl2, right? And that's aqueous, right? And we're trying to write a balanced equation for that. So again, we look at the cross products, right? Oops, sorry, that was wrong. That's one. Why is this wrong? Why am I not worried about any product that might form between lithium and copper?
Because
They're both positively charged.
Exactly right. They're both positively charged, right? We're not going to have a reaction between two positively charged ions, right? So we're always putting the cation together with the anion. So my possible products here are going to be lithium chloride and copper nitrate, right? So these are possible products. So then I go to my solubility rules and I see, lithium chloride, always soluble. Copper nitrate, soluble, right? So therefore, we're going to write no reaction, okay? No reaction occurs between those two. Does that make sense? A couple of questions here. Diana.
Do they have to be, do we have to have a soluble and an insoluble for there to be a reaction?
You need to have at least one soluble one. You could have two sorry, my bad. You have to have at least one insoluble one.
So then if you have two soluble ones, that's when we have no reaction.
Correct. If you have one insoluble, you have a reaction. If you have two insoluble, you also have a reaction. But if you have no insoluble ones, then there's no reaction.
Okay, thank you.
You're welcome. Javier?
Yeah, my question is, how did you know that lithium nitrate was an aqueous solution?
How did I know that lithium nitrate, what?
Was an aqueous solution.
Oh, yes. So the equation told me that, right? Write an equation for the reaction that occurs between aqueous solutions of each of the following. But I also know that because lithium nitrate is itself soluble as well. So I know that if I have lithium nitrate in water, it's going to be an aqueous solution.
Okay.
Okay? Good question. All right, let's look at the next one. Sodium hydroxide plus iron 3 bromide, right? FeBr3. Again, we have to write neutral formulas for these, right? and these are both going to be aqueous. And then we're going to say, okay, what are the possible products? We're going to look. One would be sodium bromide, NaBr, right? And the other one's going to be iron hydroxide, Fe, and it's iron 3, right? So it's going to be FeOH3, right? Those are my possible products. And then I look at the solubility rules and I say, aha, sodium bromide, what do I know about that? Soluble or insoluble?
Soluble.
Soluble, so that's not going to be a product. What about iron 3 hydroxide?
It's going to be insoluble.
Insoluble, correct, right? Because hydroxides, right? Hydroxides are generally insoluble, and iron is not one of the exceptions, right? So that's going to be insoluble. So then I go, aha, I'm going to have a reaction. What are the products going to be? FeOH3 solid. I write the solid there, right? The S to show that that's my precipitate. Plus NaBr, but that's going to just be aqueous, right? Because that's not a precipitate, right? So this is my precipitate. Does that make sense? Javier, did you have another question?
Yes. My question is, when having two aqueous solutions and you mix them and both are soluble, why wouldn't it mix with the other anion or cation?
If I have two solutions and they form two soluble products,
Yeah.
then this would be solid and this would be solid as well. I'd have two precipitates.
Oh, okay.
Okay? All right. And then lastly, iron 3 sulfate. So FeSO4. Now we got to be careful writing the formula for iron 3 sulfate, right? Because, sorry, is it iron 2 sulfate? It's iron 2 sulfate. So iron is 2 plus because of the 2, and sulfate is 2 minus, right? So we know it's 1 to 1. So that's fine, just like that, right? And then that's going to it's saying that's reacting with silver nitrate. Ag is +1, silver nitrate's -1, so that is 1 to 1. So there are my two reactants. My possible products are what? Iron nitrate. And now, since iron is +2, right, I'm going to need 2 nitrates to have a neutral compound. Oh, actually, let me back up for a minute. I forgot something on this reaction. What did I forget to do? What's wrong with this reaction as I've written it?
You forgot to balance.
It's not balanced.
I forgot to balance it. Thank you. So let me just go back. We'll come back to this in a second. I forgot to balance this. In order to balance this, I'm going to see, I have 3 hydroxides. So what do I need here?
Need a 3.
I need a 3. And I have 3 bromides, so I need a 3 here. And, oh, no, sorry, not there. I need a 3 here. And I think that does it, right? 3 nitrate, 3 sodiums, 3 sodiums, 3 hydroxides, 3 hydroxides, 1 iron, 3 bromines, and 3 bromines. All right, don't forget to balance it. Don't do what I just did. Always remember to balance it. Okay, let's come back down to this one. So we have iron nitrate as a possible product, and it's going to be FeNO3 right? Because it's iron 2 plus, yeah? And then we have the other possible product is going to be what? Silver sulfate. And since sulfate is -2, I'm going to need 2 silvers. All right, so it's silver. Those are my possible products. So then I go to my solubility rules. I say, okay, what about iron nitrate? What do I know about that?
It's soluble.
It's soluble, so that's not going to be a precipitate. What about silver sulfate?
It's insoluble.
It's insoluble, right? So there's my precipitate, right? So I'm going to have Ag2SO4 solid plus FeNO3 to aqueous. Oops, ran out of room there. But that should be aqueous right there on the end. Okay. And then this time I won't forget to balance it, right? What do I need? I have one iron, one sulfate, so I'm good there. I have 1 silver, 2 silver, so I'm going to put a 2 here, right? And then I have 2 nitrates and 2 nitrates, right? So that's balanced. And of course, this is my precipitate. Does that make sense? You ready to try one yourself? All right. Here you go. Try that one. Okay, about 10 more seconds. Try to finish up the next 10 seconds or so. Okay, very nice. The majority of you got that. The correct answer is C. Most of you got that, so nice work. Basically what you want to do is you go and you look at the cross products, right? Silver chloride and sodium nitrate. You look at the solubility rules and you can see that silver chloride is a chloride. So you look here, chlorides are generally soluble, but silver is an exception, right? So if you were to write this reaction, you'd write AgCl solid plus sodium nitrate aqueous, right? And the solid here tells you that this is your precipitate. All right, does that make sense? All right, very good. So those are precipitation reactions. That's one class of these aqueous reactions that we want to be able to write equations for and predict. Okay. Diana, do you have a question?
Yes, I did. When it precipitates, is it always going to be a solid? What does
Yes,
that mean?
correct. That's what that means. Yep. Yep.
Okay.
Perfect. Okay, before we move on to the other two types of reactions that I want to get to, I want to talk a little bit about different types of equations that you can use to represent these reactions. All right, what we've used so far is what's called the molecular equation. Even though ionic compounds don't really contain molecules, so this is kind of a funny misnomer, but basically in the molecular equation, you write neutral formulas for each of the compounds no matter what, right? So for example, in this reaction, potassium hydroxide aqueous, magnesium nitrate aqueous goes to 2 potassium nitrate aqueous plus magnesium hydroxide solid, right? So you write solid here to indicate that's the precipitate, right? But everything else is written as aqueous, and you write it as neutral formulas for each compound. Another way to represent this reaction that is actually a little more accurate in terms of what's actually happening in the solution is to write the complete ionic equation. So the complete ionic equation actually shows those compounds that are dissociated into ions, it shows them as ions, right? So in other words, is KOH present in water as potassium hydroxide units? No. It's present as potassium and hydroxide ions that are separated, right? Because it dissociates in solution. Remember how we talked about strong electrolyte solutions, right? This is an example of a strong electrolyte solution. Any soluble ionic compound is going to be a strong electrolyte solution, right? So it actually exists like this. And again, magnesium nitrate, it's soluble, right? And so does it exist with magnesium nitrate units? No, right? Instead, you have magnesium ions and nitrate ions, all right? The only thing that exists together is the solid because it's formed a precipitate. So magnesium hydroxide is a solid and you keep that together. Potassium nitrate is soluble, so you separate those as well. This is called the complete ionic equation, all right? Now, what you can do in a third way of representing these reactions, which is called the net ionic equation, is you can get rid of ions that are called spectator ions. Spectator ions are ions that are the same on both sides of the equation. Okay, spectator ions are ions that are the same on both sides of the equation. So if we look here, you see that on this side you have potassium plus, and on this side you have potassium plus, right? So I can cross out the potassium pluses because they're the same on both sides. Similarly, on this side I have NO3 minus, and on this side I have NO3 minus, and there's no change, right? So I cross those out. If I cross out those ions, what am I left with? 2OH minus plus magnesium 2 plus goes to magnesium hydroxide. And that's called the net ionic equation. All right, the net ionic equation shows the associated compounds as ions and eliminates all spectator ions, right? These are the spectator ions. Taylor.
So if there's no reaction, you won't have a net ionic equation?
Correct.
Okay.
Good question. Yeah, if there's no reactions, there would not be a net ionic equation. Taylor, yeah, you're welcome. Any other questions? Does that make sense? Michael. Let's see. Michael, are you there? We can't hear you if you are. Oh, there you are. Michael? I can see you, but yeah. Go ahead. No, I can't hear you, Michael. All right. Sorry about that. You can type your question in the chat if you'd like. Okay. So let's try this. Let's write a net ionic equation for this reaction. 2 AgNO3 aqueous plus magnesium chloride aqueous goes to 2 AgCl plus magnesium nitrate. So let's start with the complete ionic equation, which would be 2 Ag plus aqueous plus 2 NO3 minus aqueous. Remember that this 2 extends to both of those, right? Plus magnesium 2 plus aqueous plus 2 Cl minus aqueous all goes to silver chloride solid. I keep those together, right? Why? Because that's a solid. Yeah. And then plus magnesium 2 plus aqueous plus NO3 minus. I need 2 of those aqueous. So there is my complete ionic equation, right? And then to get to the net ionic equation, I'm going to cross out and get rid of the spectator ions. What are the spectator ions? The ions that are the same on both sides of the equation, right? So here I have nitrate and nitrate. Those are the same on both sides. And then I have magnesium and magnesium. Those are the same on both sides, right? So then my net ionic equation would be 2 Ag plus, right, whatever's left over, plus 2 Cl minus, right, goes to 2 AgCl solid. All right? Does that make sense? Javier, Javier, do you have a question?
Yeah, I still don't understand why, can you hear me?
I can. You're a little broken up, but I think I can hear you.
Let me see. Oh, I was saying that I still quite don't understand why the magnesium and and the 2NO3 don't react.
Why they don't react? Because that's so. If you look at this equation, right, the magnesium nitrate is soluble, right? So if you look back at the solubility rules, right, you look at nitrates, they're always soluble. So magnesium nitrate, it does not form a insoluble substance. Only the insoluble substances will show up as precipitates.
And that's because they're in presence of water, right?
One more time.
And that's because they're in presence of water.
Correct. Yeah, they're all aqueous. Yep. Yep.
Okay, thank you.
Okay, you're welcome. All right, so go ahead and try this one yourself. Okay, I'm gonna give you about 10 more seconds. I know some of you may not finish, but I'm just gonna cut it off here in about 10 seconds. Okay, so most of you put B, and that is in fact the correct answer. So nice job. Basically, for those of you that didn't get to finish, it does take a little bit of time. So you got the calcium nitrate and the sodium carbonate, right? And then you look at the possible products, right? And what are they going to be? Calcium carbonate and sodium nitrate, sorry. And then you look at the solubility rules and which one is insoluble? The calcium carbonate, right? So you know this is going to be calcium carbonate, and that's going to be solid, plus sodium nitrate, and that's going to be aqueous, yeah? And then anything that's aqueous gets broken up into its ions, right? Oh wait, what did I forget to do again? I forgot to balance this. How am I going to balance this? I have a 2 here. I have 2 sodiums here, so I need 2 there. Calcium 1, carbonate 1, nitrate 2, so that's good, right? So that's balanced. And then you got to break up anything that's aqueous into the ions and then eliminate the spectators, right? So that's calcium 2 plus, aqueous, plus 2 nitrate, aqueous, plus 2 sodium, aqueous, plus CO3 2 minus, aqueous, goes to calcium carbonate solid, plus 2 sodium plus, aqueous, plus 2 NO3 minus aqueous, right? And then you cancel out all of the spectator ions, right? So what are they? Nitrate and nitrate, right? And then also sodium and sodium, right? So what are you left with? Calcium 2 plus, right? Plus carbonate right here goes to calcium carbonate. All right, does that make sense? Questions? Awesome. All right, let's move on to acid-base reactions. So in an acid-base reaction, you have an acid and a base that neutralize each other, forming water and a salt, right? So remember acids, we talked about them a little bit before when we were talking about nomenclature of molecular compounds, right? So remember acids have certain properties. They have a sour taste. You find them a lot of time in citrus fruits, right? Like in lemons and limes, for example. They also tend to dissolve metals, right? And we're typically going to write them in the form of some hydrogen, right, plus perhaps a polyatomic ion, like that. That's nitric acid, right? And then HCl would be another example. That'd be hydrochloric acid, right? But we're going to recognize them by that H out in front, okay? Here's some examples of a bunch of different kinds of acids. You don't have to memorize this. I just throw this out there. Nitric acid is one we've seen before. Sulfuric acid. Hydrochloric acid. Hydrochloric acid is the acid that's in your stomach. So another property of acids is a sour taste. So sometimes when you have acid reflux, you get the sour taste in your mouth, right? And that's because of the acid from your stomach that has come up to your mouth. I know that's kind of gross, but that's the way it works. Acetic acid is the acid that's in vinegar, okay? And then a few other acids here. Bases are generally going to contain the hydroxide ion or are going to form the hydroxide ion when they go in the solution, all right? And here's some example of bases. Sodium hydroxide, potassium hydroxide, sodium bicarbonate. This is the base that's in baking soda, all right? So let me just remind you of the definitions here. Acids produce H plus in solution, right? Bases produce OH minus in solution. So what happens when you get an acid and a base together, right? The acid and the base can react. The H plus can react with the OH minus, and what does that form?
Water.
Water, right? HOH, which is water. Okay? So acids and bases tend to neutralize one another. Okay? And the general form of those reactions is acid plus base produce water and salt. Okay? So let's look at some examples. Here's HCl and NaOH. Now, again, we're going to follow the same pattern that we did before. We're going to combine the anion of one, the cation of one with the anion of the other, and the cation of the other with the anion of the one, right? And what you're going to see there is that the products are going to be sodium chloride, which is just going to be aqueous, but the other product is HOH, which is H2O, right? So we're going to write this whole equation like this. HCl aqueous, NaOH aqueous, H2O liquid plus NaCl aqueous. Notice the pattern. Acid plus base produces water plus a salt. And by salt, I mean any aqueous ionic compound. All right, so you're going to have some aqueous ionic compound that ends up being dissolved. Okay? So let's do another example. Write the equation for the reaction of aqueous nitric acid. Okay, so again, we have to remember our nomenclature. There's aqueous nitric acid with aqueous calcium hydroxide, right? And so when I put together, again, this and that, and this and that, right, I get H2O plus, because that's HOH plus calcium nitrate, right? And of course I have to balance that. Let's see, I need a 2 here, and I need a 2 here, and I think that balances it, right? But again, notice the pattern: acid, base, water, salt. Yeah, and what did I forget here? I forgot my liquid and my aqueous. Does that make sense?
Why is the water not aqueous?
Oh, because it's not dissolved in water, it is water.
Okay, that kind of makes sense. Okay.
Yeah. Yeah.
Okay. Oh, so since it is water, then
It's just part of the liquid.
it would just be a part of it. Okay.
Yeah. Yeah.
Thank you.
Megan.
Hi, can the water ever turn into a gas in these kind of reactions?
Not typically, because you're typically carrying these. I mean, it could theoretically, you know, if you had a lot of acid and base being mixed together, it could produce a lot of heat, which would then evaporate the water. But that's not really an example of what's called a gas evolution reaction, because the gas was produced by the heat, not by the mixing of not by the anions and cations of the two solutions.
Okay, got it.
Okay.
Thank you.
Javier?
Yes. So in an actual reaction of this compound, like if in a lab, when getting the reactants, the water and the salt, if we leave it there, we can separate the water from the salt.
It depends. Usually the salts are going to be soluble, so they're going to be mixed in with the water, and you can't separate them unless you boil off the water or something like that.
Okay. Okay. Thank you.
Abe?
If we were to write the net ionic equation for, I guess, like this,
Yep.
this equation just given, we couldn't, I guess, like sort of like break down the H2O, right? We'd just leave it as a liquid, almost like if it were an insoluble substance.
Yeah, the net ionic equation for all acid-base reactions is going to look like this.
Got it.
Okay. Good. Okay. Let's have you try one. Go ahead and try this one. Okay, so I'm going to stop it right there. Most of you put A, which is indeed the correct answer, so nice job. Really briefly, right, you have HBr, MgOH, again, boom, 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 right? Same pattern as we've been doing all along, right? So HOH is going to be your water, and then MgBr is going to be your salt. And you notice as it's acid plus base goes to water plus salt, right? And then lastly, you just balance it by putting the 2's there, okay? All right, very good. Any questions on that? Okay, let's move on to gas evolution reactions. So that's the third class of reactions that follow this pattern, right? And again, notice that we're doing the same thing every time, right? We have AX plus BY goes to AY plus BX, right? We are always combining the cation of one with the anion of the other, and the cation of one with the anion of the other, right? And then we're basically going to ask a question about these possible products, right? These are our possible products, right? Are the possible products, are any of the possible products A, an insoluble compound, right? If any one of them are an insoluble compound, then what kind of reaction do we have?
Precipitation.
Then we have precipitation, right? That leads to precipitation reaction. For acid-base reactions, we're asking, are any of those possible products HOH, right? Which is the same as water, right? If any of those possible products are HOH, then what kind of reaction do we have?
Acid base.
Correct.
Acid
Then we have an acid-base reaction, all right? And now we have a third category, right? Is RAY or BX any of these possible things? And the things we have to look for, there's 4 things, and you just have to know these. H2S, SO2, CO2, or NH3. Okay? If AX or BY are any of these, then we have a gas evolution reaction. Right? A reaction where you mix 2 substances and you produce a gas. All right? So here's an example. You have sodium bicarbonate plus HCl, and that's going to form H2O plus NaCl plus CO2. CO2 is the gas. But notice what happens here. If I look at my initial reactants, right, and I say, all right, NaHCO3 plus, oops, sorry, I blew this. I made a mistake here. This should be, what I'm looking for here is not CO2, is H2CO3, and what I'm looking for here is H2SO3. All right, these are actually the things I'm looking for. If AY or BX or any of these 4 things right here, okay? H2S, H2SO3, H2CO3, or NH3. So for example, here I have NaHCO3, aqueous, plus HCl, aqueous. And now notice when I look at my possible products, right? My possible products are NaCl and H2CO3. So when I see that H2CO3, I go, that's one of these 4. So then I know I have a gas evolution reaction. Okay, I'm looking for that as a gas evolution reaction. All right, now what happens is that this H2CO3 actually breaks down into H2O plus CO2. It doesn't stay as H2CO3. All right, so you just kind of think of this as an intermediate product. So the real products of this reaction are NaCl plus water plus CO2. This is gas, this is liquid, and this is aqueous, right? And there's my gas, which is the gas evolution, which is the thing that's bubbling. Okay? So here is a chart of all those intermediate things that you're going to see. Oh yeah, and I forgot, and I made it. This one should not be NH3 either. I accidentally put the gases instead of the intermediate products. NH4OH is the thing you're looking for there. Okay, so these are the intermediate products that you're looking for. So in other words, when AY or BX form any of these 4 things, then you have a gas evolution reaction. Here are the 4 things you're looking for, right? And here are the gases that are evolved. All right. So H2CO3 as an intermediate product breaks down into H2O and CO2. H2SO3 breaks down into H2O and SO2. And NH4OH breaks down into H2O and ammonia. All right. So you kind of got to know this table, and you got to know what those products are. All right. So let's do a quick example. And we'll just do this one. Well, I'll just open this up and we can do it. We can do it together. When two ionic compounds react, the reaction sometimes results in a gas phase product. Which of these ions can lead to a gas evolution reaction? So in other words, which of these ions, when you see it in a compound or you see it in an intermediate product, should you think, aha, this might be a gas evolution reaction?
Should be C, right?
Yeah, it should be C, CO3 2 minus, right? So if you go back to here, right, when you see CO3 2 minus and it combines with H, then you form this intermediate product H2CO3, which breaks down into H2O and CO2. Okay, so this perhaps is the most complicated of the three kinds of reactions that we've talked about, but it's really not that bad. All you got to remember is if any of these two things, right, AY or BX, any of the cross products, if they're one of these four, right, then you should go, oh, ding, 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 ding. That is a gas evolution reaction. All right. What's the gas that's evolved? It depends on which four of these you have, right? If the intermediate product is H2S, then the gas is H2S. If the intermediate product is H2CO3, then the gas is CO2. If it's H2SO3, then it's SO2. If it's NH4OH, then it's ammonia, NH3. Okay, our last class of reactions that I want to look at don't follow this same pattern, and you don't have to predict, you don't have to be able to predict them. I just want you to be able to identify them, okay? And this class of reactions is called oxidation reduction reactions. Emily, did you have a quick question?
Just really quickly, so when we're writing gas evolution reaction,
Yes.
should we always write the final version where we break it down into H2O plus
Yep.
the gas?
Yep. So if you see any of these intermediate products, right, what you should write in your reaction is not the intermediate product, but the final product.
Right, okay.
Yeah.
Got it.
Good question. Okay, our last class of reactions, oxidation reduction reactions. So oxidation reduction reactions are super common, both in solution, which is what we're going to focus on here, but they can also happen outside of solution. So for example, when I combine hydrogen and oxygen to form water, I get a big explosion, and that's an oxidation reduction reaction. When I combine sodium and chloride to form sodium chloride, that's an oxidation reduction reaction. Oxidation reduction reactions involve the transfer of an electron. All right, Abe, I'm going to save your question until after class only because I only have 5 more minutes and I got to just at least introduce this last topic. So I'll get to you in just a minute. So for example, when sodium reacts with chlorine, sodium will give an electron to chlorine. We say that sodium is oxidized. Is the loss of an electron. Reduction is the gain of an electron. Okay. In this case, sodium gives an electron to chlorine, right? And that becomes a positive ion. Chlorine becomes a negative ion, and they attract each other through that ionic attraction. Sometimes it's easy to tell if you have an oxidation reduction reaction, right? Because here you have a metal and a non-metal. What do you know about metals? What do they tend to do in chemical reactions?
Lose electrons.
And to gain an electron.
Metals tend to lose electrons, right?
Sorry, lose.
Yeah, lose electrons. And what do you know about non-metals?
Gain.
They
And
tend to
again, So when you combine a metal and non-metal, you have a perfect match, right, for an oxidation reduction reaction. The metal loses an electron, so the metal is what? Oxidized or reduced? Oxidized. The metal's oxidized, right? The non-metal gains an electron, so the non-metal is reduced, right? Very good. Now, sometimes you can have oxidation reduction reactions between compounds that, between elements that are not, that are not metals and non-metals. So for example, when hydrogen reacts with chlorine, you get HCl, and in the HCl, this side of the molecule is more positive, this side is more negative. Why? Because even though this is a covalent bond, the electrons are not evenly shared, okay? So the chlorine has effectively gained some of the electron density from the hydrogen, even though there's no transfer of electron completely, all right? So how do we keep track of these kinds of reactions? In other words, how can we predict a redox reaction, or sorry, not predict, how can we identify a redox reaction when I have a reaction between two non-metals, all right? We can do that with something called oxidation states. So we can assign oxidation states to any element in a compound. And an oxidation state is the charge an atom would have if shared electrons were assigned to I'll say the least metallic element. Oxidation states would be the charge an atom would have if shared electrons were assigned to the least metallic element, okay? Now, this is not always easy to predict, so we have some rules that we can follow to assign these oxidation states. So let me give you the rules real quick, and then stick with me. I'm going to go over by maybe a minute or two just to show you an example, all right? So here are the rules. Number one, we've got our fresh piece of paper. Number one, the oxidation state, so let's see, oxidation state rules. The oxidation state of an atom in a pure element is 0, right? So if I have elemental sodium, for example, or elemental chlorine, for example, right? The oxidation states of the atoms are 0, okay? Remember, this oxidation state is kind of it's kind of a fictitious charge. It's kind of a charge it would have if the electrons went to the atom that attracted them the most, all right? So pure element is 0, that's rule 1. Rule 2, the oxidation state of a monoatomic ion is equal to its charge. So for example, Na plus, S2 minus, right? The oxidation state of Na plus is +1, of S2 minus it's -2. Okay? The sum of all oxidation states, the sum of all oxidation states in a neutral molecule is 0. In an ion is equal to the charge of the ion. And so what that means, if I have something like HCl, for example, the oxidation state of hydrogen is +1, the oxidation state of chloride is -1. So when I sum those together, I get 0, right? Because HCl is neutral. Okay? If I have something like OH minus, the oxidation state of oxygen is -2, hydrogen is +1. So when I sum them together, that's -1. So notice that the oxidation states for a neutral molecule add up to 0. For an ion, they add up to the charge of the ion. Okay? And then rule 4. In their compounds, metals have positive oxidation states, and some metals always have the same oxidation state. So group 1A metals are always +1. Group 2A are always +2. All right, so for example, if I have, let's say, potassium chloride, right? The potassium is +1, and therefore the chlorine must be -1. Similarly, if I have magnesium bromide, the magnesium is +2, and the bromine is -1. Notice in this case, the oxidation state is actually equal to its charge. Okay, it's not always the case, but for these metals, it is. All right, and then finally, for non-metals, assign oxidation states according to this table. All right, and this table is hierarchical. And what does that mean? That means that things on the top of the table take precedence over things at the bottom. Hierarchical. Top takes precedence over bottom. All right, I know that's a lot, and I know I'm totally out of time. I'll do a couple of examples, and then we'll be done. All right, and yes, the rules are in the book. All right, so bromine, what is that? That's a pure element, so what's the oxidation state of bromine and bromine?
0.
0.
0, correct. Potassium plus, that's a monoatomic ion. Its charge is +1. So what's the oxidation state of potassium plus?
+1?
+1, correct. Okay. To the bottom here, let's write down lithium fluoride. So now we have our first compound, right? We see here that it has lithium. Lithium is a metal, and it's a group 1A metal, so what's the oxidation state of lithium?
+1.
+1. And therefore, since it has to sum to 0, what do we know about fluorine?
Has to be a -1 then.
Correct. All right. Now let's go let's look at CO2. Now we go down our list for CO2. Sorry. We go through all of these and we don't find either carbon or oxygen, right? Until we get to number 5 here. So now we have to go to this hierarchical list. So what comes first on this list? Well, there's only one of these is on this list, and that's oxygen, right? Oxygen is right here. So what's the oxidation state of oxygen?
-2.
-2. And then we're going to use this rule that the sum must be 0 to find the oxidation state of carbon, right? So there's 2 -2s. So what must be the oxidation state of carbon? +4, correct. You see that? I know I've gone through this very, very quickly. Let's just do a couple more, and I know we're out of time if you need to go. please feel free to go. CH4, it's right here, right? Again, we get to the bottom of the list, and what do we assign first here between carbon and hydrogen?
Hydrogen we assign first, right?
Yep, +1. So then what's carbon?
So it'd be a -4 because there's 4 hydrogens.
Correct, be -4 because it has to sum to 0, right? More examples. Let's do SO4 2 minus. Right. So we look at all these and we go, sorry, we look at all of our rules. We get to nothing except until the bottom we get to non-metal. So then we go to this hierarchical list. What do we get to first as we go down this list? Oxygen or sulfur?
Oxygen.
Oxygen. So oxygen is this one, sulfur is this one. So it says to assign oxygen -2. Sulfur would also be -2, but that can't be the case, right? So oxygen takes precedence. So oxygen, because it's higher on the list, -2. There's 4 oxygens, so together they're -8. The total charge is 2-. So what's the oxidation state of sulfur here?
+6.
+6, correct. All right. Okay, we're really out of time. I apologize for going over. It is 3:27. We'll pick up here next time, but I'm going to go ahead and officially end class right now. And for those of you that want to stick around and ask questions or anything, you certainly can. And I'm going to stop the recording.